Hello everyone. My name is Ram Reddy,
And I'm Eric.
and today we're going to be talking about an introduction to Bayesian networks. So, what exactly is a Bayesian network? So, a Bayesian network is something that can build models from data, and more specifically, a probabilistic graphical model. And what that is, it is something that can show conditional dependence and like structure based on random variables. So as you can see in the picture in the bottom right, there are 5 random variables here: the alarm on, overslept, bus late, and on time. And these variables can depend on the previous linked variables. So for example, overslept can depend on alarm on. So if the alarm is off, then the person might oversleep. And for example, for on time, if the bus is late and if a person oversleeps, then they have a higher chance of being on time. And a Bayesian network uses the Bayes theorem, and I'm not going to go into it right now, but it's basically something that can help us calculate probability based on the variable distributions. So comparing Bayesian networks to neural networks, Bayesian networks have better accuracy because they have a complete data set, and since they're random, they have a higher chance of having a normal distribution of that certain variable. It's also easily adaptable, meaning that it's easier to reconstruct it in a different way because the data is already in distributions. It's easier for us to actually create a model from that. It's also more easily understood and thus evaluated because, like as you can see in the bottom right, it was very easy to understand uh, what this figure was doing. And of course, not all models will be as simple as this, but uh, they do have, it's much easier to understand them than a bunch of weights like in a neural network. And the labels on this helps a lot with that. And also, you don't need to know multivariable calculus to understand it. So for neural networks, it has a much faster model evaluation time uh, because it only uses weights, and these weights don't usually change after the first construction, while the Bayesian network can use much larger distributions, which makes the evaluation time much lower for inputted data. And neural networks can also be constructed with incomplete data, which is a huge benefit because normally you don't have complete data sets to train on. Whereas in Bayesian networks, you need to have a complete data set with distributions, or else it won't work properly. So, yeah. So what can Bayesian networks be used for? Bayesian networks are really good for taking an event and predicting what a possible cause is, as we saw in the previous models before. Uh, we could see like the possible causes of an event occurring, and the same thing in the picture in the bottom right here. So we have diseases and symptoms for each of those diseases, and we can use the symptoms as an input and predict the likelihood of a patient having a disease. And this leads us to our next point, decision making under uncertainty. Like, of course, like when we input symptoms into a model, we're not sure of a certain disease actually being that the patient having that certain disease. Like as you can see, difficulty breathing is a symptom of both left heart syndrome and lung cancer. So what a Bayesian network can do is give us a range of possibilities. And these range of possibilities allow us to know if the output given is actually something that is right or not. Because from that range, we can also conduct standard deviations of the possible outputs and see if the outputs are a viable source of information. They're also great for anomaly detection because in a Bayesian network we create it out of distributions of the variables, and if we input certain things into the so let's say like someone eats like 100 pounds a day or something, that's like definitely an outlier because um, in a Bayesian network we would see if these like variables, if the variables given are like uh, really high or really low. And there's also a great way to understand a model. So since it's graphical and also has labels, it's like anybody can understand it. And they're also really efficient. Okay, so now I'm going to talk about Bayesian probability. And the reason I'm talking about Bayesian probability is because it is important to understand how Bayesian networks work. So I'm going to talk about like some of the basics you need to know about Bayesian probability to understand the more advanced concepts. So in Bayesian probability, each variable is represented by an uppercase letter like A and B, as you can see in the slide. And to get the number of possible values in a variable, we would do, which is denoted by pipe A pipe. So that basically means like if we have a variable like is sick, possible values is true and false, and it's the same thing for like a quantitative variable as well. And the variable can hold whatever it is. Like for age, it would be the age of that person. And then we have a set of variables, which is denoted by a bold uppercase letter like X. And a number of variables in a set is denoted by pipe X pipe, which is just the number of variables in the sets. All variables in the Bayesian network is denoted by U, which is also like universal. And to denote the probability of a variable, we can do P parenthesis A parenthesis. We can also do a joint probability, which is say basically a union notation, as you can see in this Venn diagram right here, in the bottom right, which is denoted by P parenthesis A comma B parenthesis. Then we have a conditional probability of A given B, which is basically the probability of A intersection B and probability of B. And that is denoted by P parenthesis A pipe B parenthesis. So now I'm going to talk about Bayesian graphs. Bayesian graphs are what the type of graphical models we've showed before, like with the diseases and symptoms, and they're based on DAGs, which are directed acyclic graphs. These are graphs that are directed to, like, each node is pointing to another node, and they do not contain any cycles, um, and all edges travel down, so they're topographically ordered, and they form no loops, as we said before. And uh, Bayesian graphs also should reflect knowledge that can be easily interpreted, uh, like the diseases and symptoms that could easily be interpreted by just seeing it. And the graphs are made up of a set of nodes, which is called structural specification, and each node is represented by a variable like age or gender. And there are two types of variables, discrete and continuous. Discrete being something that has a finite number of possibilities. Like for gender, for example, a person can be male or female. And there is a continuous variable, which is the opposite. It has an infinite number of possibilities between two numbers. So for example, age, a person can be 16 or 17, but like there's an infinite number of possibilities in between those two numbers. So a person can be like, uh, let's say 16 years old, 7 months, 5 days, 4 seconds, and on and on. And as you can see, there can be an infinite number of possibilities that exist for that variable.
All right, so at the center of Bayesian probability is Bayes' theorem, which is a pretty simple probabilistic equation. So there are two prerequisites for Bayes' theorem to apply. One, that the factors are independent, and two, that the factors have an equal effect on the outcome. So this should just be a review of research statistics, but the probability of A given B is equal to the probability of B given A times the probability of A divided by the probability of B. So this can be generalized to our data set, the probability of Y, an outcome happening, given X, the set of observations that Ram talked about earlier, which could be like a medical observation or just any kind of observation, is equal to the probability of those observations given the outcome times the probability of the outcome divided by the probability of those observations. So Bayes' theorem is generally applied in medical predictions, but another common real-world example is in spam detection. So in this example, we're trying to calculate the probability that an email is spam given the words in that email. So we can see here the probability of an email being spam given the words is equal to the probability of the words in the email being spam times the probability of having a spam email in any of your emails divided by the probability of having those words in any of your emails. I hope that made sense, because now we're going to move on to expanding this equation. So we expand it using the chain rule, since generally you're not going to have a single variable as your observation. So this can be expanded like this. And we can introduce a proportionality. So the probability of Y given these words is proportional to the probability of Y times the summation of the probability of those variables given the outcome. And then we use argmax to calculate the greatest probability. So at the backbone of Bayes' theorem is a set of distributions, as you can see here. Distributions are a critical feature of Bayesian probability since it updates these distributions using hyperparameters such as standard deviation and mean instead of a conventional neural network which just uses a single weight value. So you may be wondering how these probabilities, such as the probability of words or the probability of spam, is calculated. Well, they are calculated using basically this structure. The likelihood, in addition to the data, which can be words from a new email, plus the prior distribution, are culminated in Bayes' theorem and update the prior distribution to form this posterior distribution. This is basically how Bayes' theorem learns. This is how it updates its probabilities, and this is really the backbone of Bayesian probability. So in the previous slide, we discussed the general structure in which a Bayesian network, quote unquote, trains. But now we're diving into a deeper understanding of different methods in which we can train Bayesian networks. So the first important thing to note is that Bayesian networks do not use weights or biases. It is purely based on the data and updating those distributions. Okay, so in the same way that a conventional neural network has supervised and unsupervised learning, a Bayesian network has manual construction and automatic construction. So manual construction is knowledge driven and requires purely upon the knowledge of the programmer to make a directed cyclic graph that Ram talked about earlier. And they use that to calculate the probability distributions for every node and the dependencies between those nodes. So this requires a lot of manpower, and it is very accurate, but it cannot be applied to larger data sets in which manual construction is physically impossible. So in that case, we turn to automatic construction. So automatic construction is data-driven instead of knowledge-driven, and basically relies upon the given data to calculate the locations of those nodes and the dependencies that lie between them. All right, so there are three parts to automatic construction. The first part being inferring unobserved variables. And this is kind of basically what we talked about in the previous slide. The network updates knowledge of the state of its variables when new evidence is observed. So for new evidence variables, it updates the prior distribution using Bayes' theorem and calculates the posterior distribution. This method, which we talked about earlier, is called a probabilistic inference. The second part of automatic construction is parameter learning. So since the parameters for automatic construction are not known, we estimate them. So in order to estimate the parameters, we use the posterior distribution and approximate the most likely values that they could be. This is generally implemented using maximum likelihood estimation, but we won't really get into that in this lecture. Okay, so the third part of automatic construction is structured learning. So using automatic construction, we are given data, which is just a series of nodes dispersed randomly throughout this network. That's called a skeleton structure. So structured learning, the process of structured learning, is basically meant to derive the direction and location of dependency arrows that connect those nodes, or like that describe causation within the structure. So for manual construction, those dependencies are inputted by the programmer, but automatic construction relies upon a set of machine learning neural networks or other algorithms to systematically determine the orientation and location of these dependency arrows while maintaining the topographical order of going from up to down and maintaining the acyclic structure. So the most common implementation of data mining is, for example, in a research database in which data mining is used to find causal relationships between nouns within a research article to provide the best recommendations for a researcher's search criteria. So moving on, Bayesian networks are rarely used by themselves for classification or regressive problems, and they're generally used with other algorithms such as before, which help create these dependency nodes within the Bayesian network. So Bayes' theorem can be implemented into Bayesian neural networks and Bayesian convolutional neural networks. Now, we're not really going to go too deep into what those are, since the main difference between them is pretty much the same difference between neural networks and convolutional neural networks. But we are going to talk about the purpose. So the main purpose of implementing Bayes' theorem is for anomaly detection, to decrease standard variation, and to increase confidence in the model's predictions. So you may be wondering what these silhouettes are on the bottom. So using a Bayesian neural network, some researchers trained it to calculate regressively the heights of silhouettes of babies. And then in the testing data set, they threw in a silhouette of the spider. In a conventional neural network, the model would predict regressively that the spider's height is probably about 3 feet tall. But in a Bayesian neural network, using Gaussian distribution, it can calculate the confidence of this decision and the standard deviation from this picture compared to the other silhouettes. And because of this, the model is able to create this graph, predicting accurately that the height of the spiders is indeed shorter than the height of the babies, without any spiders being inputted into the training data set. This basically shows the versatility of Bayesian neural networks and how powerful they can be in detecting anomalies in data sets and really increasing the accuracy of any neural network. All right, so a method of implementing Bayes' theorem into Bayesian networks is Bayes by backprop, which was introduced by Blundell et al. In 2015, and it basically replaces backpropagation in a neural network. So we're really emphasizing this point that instead of a simple point weight estimate, it updates weights based off of a Gaussian distribution. So it backpropagates using two hyperparameters, mean and standard deviation, which allows the model to calculate uncertainty estimates of actions for updating weights and biases, and thus generalizing it. So it can be implemented using a Gaussian prior, and if you want to look at some of the code for implementing a Gaussian prior, you can look at our lecture notes. And that pretty much concludes implementation for Bayesian networks.
Now I'm going to talk about the summary of everything that we've discussed so far. So a Bayesian network is made out of nodes and edges, and it can be constructed manually or automatically. And overall, it's a great way to represent random variables that may have relationships. And finally, Bayesian networks use distributions to model probability, and one such example is the Bayes' theorem.
Here are our sources. Thank you for listening. And if you have any questions, just either put them in the chat or unmute yourself and ask us.
You can also find more information in the lecture notes linked, and you can also view the presentation. Yeah, thanks for listening.
Yeah,
Bye.
thank you.